Okay, we've come to the final section in Chapter 11 that's dealing with testing series for convergence or divergence. In this video, we're going to go through section 11.6, which is on absolute convergence and the ratio and root tests. Now, I do want to point out that you might be thinking that if you take all the tests that we've learned together, so the integral test, the comparison test, alternating series test, and then what we're about to learn in this video, you might be thinking that with just these tests, we're still pretty limited on the different kinds of series that we can test. And, you know, personally, when I was going through calculus, I thought this way because, for example, the two of the sections, right, two of the four sections, the first two, the function had to be strictly positive, or the terms of the series had to be strictly positive. That was a requirement. And, you know, I think about functions in general, right? You can kind of think of a series, the a sub n as a function if you replace the n with an x. Functions in general aren't positive, always positive, or even always decreasing, right? A lot of these, it's not just positive, but they need to be decreasing as well. Well, remember that, well, first of all, you could have a function that's always negative, let's say, or a series terms that are always negative, and you could just factor out a negative sign and bring out a negative sign in front of the summation, and it turns into always positive. But just keep in mind that we're only thinking about these terms as they go off to infinity. Yes, if you think about a function around x is equal to 0, like between plus or minus 10 or plus or minus 50, well, yeah, then it can do all kind of crazy things, like a polynomial, for example, or like a high order polynomial has all kind of behavior around the origin. But when you're going off to infinity, it's the function behavior is a lot more predictable. It's a lot more stable and consistent. Because for these series tests, they say that the series needs to behave in a certain way from n is equal to 1 to infinity. But in reality, like we've talked about, it's really more about you can find any n value, n is equal to 5, 6, whatever. And then from that point on, the function is always positive and always decreasing, things like that. Think about a function going off to infinity. You don't have much crazy behavior going on. It's like it's always increasing or always decreasing when you go off to infinity, or it has some sort of predictable behavior. Okay, so when you think about it from that standpoint, we actually can test a very large amount of series with what we've already learned and what we're about to learn in this video. Okay, and so there are cases like we've talked about in previous videos that, you know, you do have, even going off to infinity, you do have a function that isn't always positive or always negative. So like, think about the terms of cosine of n over n squared. That does something like this, going off to infinity. Okay, so up to this point, we don't have a way of testing a series like this, because this isn't an alternating series. And in the alternating series video in the previous section, I talked about in detail on why this is not an alternating series. So go check that out if you need. But this is not an alternating series, so we don't have a way to test something like this, a series like this. But we're going to learn in this video how we can do that. So the idea of absolute convergence, and also in combination with that, the ratio and root tests, is really going to allow us to bring everything together, bring all of the tests that we've already learned so far. And then when you add absolute convergence in the ratio and root test, then we can really test a large percentage of all of the series that you could create. So, okay, given any series, we can consider the corresponding series. So you have the absolute value, the series of not the series sum not of a sub n, but of the absolute value of a sub n, whose terms are the absolute values of the terms of the original series. Okay, a series is called a general series, sum of the a sub n's, is called absolutely convergent if the series of absolute values is convergent. Okay, so this is just a definition. We don't know what this means yet, but it's called absolutely convergent if the series of absolute values is convergent. All right, now, don't get confused here in the sense that in the opening section to this chapter, we talked about the test for divergence. And that was when you have a series. So we're talking about infinite series here, obviously, testing for convergence or divergence. You have a series And if you take the limit of the corresponding sequence of that series, then if this is going to be a convergent series, then the limit of a sub n needs to be 0. And so if it's not 0, you know it's divergent. But again, it doesn't mean that if this limit goes to 0, that the series is convergent. It could be the case that even though a sub n goes to 0, the series is still not convergent. However, if the series is going to be convergent, then the limit of a sub n has to go to 0. Don't confuse that with what they're saying here. Like they're not saying that we're not taking the absolute value of a sub n and taking the limit of that. No, they're saying that you have this a sub n series, and then they're saying that the series of the absolute values of the a sub n's is convergent. That the series is convergent, not the limit of the it's not the limit of the absolute value of the a sub n's. That not the limit of that sequence. It's this series, the series sum of the. You take the absolute value of the a sub n sequence and you put that into a series. If that series is convergent, then the original series that has no absolute value, that's called absolutely convergent. Okay, but again, this doesn't mean anything to us at the moment. This is just a definition. We call that absolutely convergent. We call a series that satisfies this criteria as absolutely convergent. Okay, it says, notice that if the sum, the series is a series with positive terms, then the absolute value of a sub n is equal to a sub n, and so the series itself is convergent. Well, yeah, obviously, right? If you have a series that's absolutely convergent, but the terms of that series are always positive anyway, well, then the series is convergent. And just to point this out, what if you had a series that was always negative? The terms were always negative, and you found that it was absolutely convergent. Then would that series be convergent? Yeah, it would. And why is that? Because think about it, okay? What they're saying is that let's imagine that you have an a sub n that's the terms are always negative. So you find out it's absolutely convergent by doing what? By you take the absolute value and you analyze that series. You do the series of the absolute value of a sub n, and you find that series is convergent. Well, okay, but what could we do with this? This is the original series where all the terms are negative. Since every term is negative, we could this is equal to, we could just take out the negative. And what we're left with is, I mean, you could write it as like a b sub n, I guess. No, you're left with this, I guess. I don't know if this makes any sense, but, right? Well, we know this is convergent. Well, all we have, so if these two are equal, right? We took out the negative sign. Well, if this is convergent, that means this converges to a value s. Well, then the whole thing is going to converge to negative s. You see? That's why if you have I've been saying, if you have a series where all the terms are negative, then that applies that as far as testing that series for convergence, you can use any of the tests that were restricted to just positive terms by just taking out a negative out front of the sum. All right, so here they give an example. This is this alternating series here. With if you take the absolute value, that's a p series with p is equal to 2, and so this is convergent. So this is absolutely convergent. But we don't know what that means. Just a definition at the moment. Okay, now here you have the alternating harmonic series, which if you take the absolute value of this a sub n, you get this is the harmonic series, which we know is divergent. So this is not absolutely convergent. But what they're wanting to illustrate here is that, so they didn't state this explicitly, but they didn't prove this. I don't think we analyzed this previously, but this alternating p series with p is equal to 2, you could assume that's most likely going to be convergent. We haven't proven it, but let's assume that this is convergent, this alternating series. Well, then it's, when we look at as far as convergent in general, when we look at it from the standpoint of absolute convergence, we see that it's absolutely convergent as well. Okay, now what they wanted to really point out here was that we know previously we've shown that the alternating harmonic series is convergent. This is convergent. However, even though this is convergent, as far as absolute convergence goes, this series here is not convergent, is not absolutely convergent, right? And so that leads into this definition 2 here. A series is called conditionally convergent if it is convergent but not absolutely convergent. Okay, so just note this. All right, and then what they state next is that, so yeah, the alternating harmonic series is conditionally convergent. Thus, it is possible for a series to be convergent but not absolutely convergent. However, in the next theorem, yeah, okay, so we're going to, you might be wondering, this might be kind of a head scratcher to you, how this is possible. How could something be conditionally convergent? We're going to talk about that at the end of this section, but especially it's a head scratcher when you consider this next theorem that says if a series is absolutely convergent, then the series itself is convergent. Okay, so I think that's more where the head scratching comes in when you realize that when you have a convergent series that's not absolute, it could be convergent but not absolutely convergent. That's possible. Then it's called conditionally convergent. But if you have a series that's absolutely convergent, then the original series is going to be convergent. We're going to talk about this in a little more depth at the end of this section, what conditional convergence means, how that's possible. But here we go though. Theorem 3. This is very powerful as far as adding to our toolbox to test series, especially when you consider the fact that you can have, this applies to cosine of n over n squared. This applies to, you can use this for any series that has negative and positive terms in it. It doesn't have to be alternating. It doesn't matter. Any series that has negative and positive terms, you can just take the absolute value of it, of the sequence formula, and then evaluate that as a series where all the terms are going to be positive, right? And so in that case, you can use the integral test, the comparison test, because the terms are always positive, right? And if that series is convergent, then you know the original series is convergent. So that's awesome. Now, just note, though, that it's not saying that if you did a test like this for absolute convergence and you found that the series of the absolute value series wasn't convergent, then that doesn't tell you that the original series is divergent. And why? Because it could be conditionally convergent, right? If you were analyzing the alternating harmonic series and you did the absolute convergence test, you would find that it's not absolutely convergent. That the series sum of the absolute value of the sequence isn't convergent. So it would be a mistake to say that, well, then the alternating harmonic series is not convergent, because we know it is. So it's only but it works the other way around though. If the series of the absolute value series is convergent, then you know your original series is convergent. So that's very powerful. Very powerful tool. Okay, so they give a proof here. And so they analyze this series here, cosine of n over n squared. And so they use it's problematic with what we've learned so far, because it's not alternating, but it has positive and negative terms. Well, take the absolute value of cosine of n over n squared. And n squared is always positive, so it's just the absolute value of cosine of n. In this case, you can do they do a comparison test compared with this p series. This is always greater than or equal to the absolute value of cosine n over n squared. We know this is convergent, so that means this series is convergent, but this means that the original series is absolutely convergent, which means that series is convergent. So that means this series is convergent. Okay, so now it says the following test is very useful in determining whether a given series is absolutely convergent. So if we come to the next page. So, okay, the ratio test. And this is, like it says, this is kind of tied in with absolute convergence. It's a way of determining if a series is absolutely convergent. So we're still talking about absolute convergence. And so, the ratio test is You take the limit as n goes to infinity of a sub n plus 1 divided by a sub n, the absolute value of that. And so this is nice because we're not, if you notice, we're not talking about we're not evaluating a series here. This is a sequence. We're taking the limit of a sequence, the sequence a sub n plus 1 divided by a sub n. So that's nice. We don't have to deal with, we're not testing a series here. If this limit as n goes to infinity is equal to L, that means it's convergent, and that L is less than 1, then the series with the a sub n series, right? That's what there's no absolute value here. Just the actual series that we're studying is absolutely convergent and therefore convergent. Okay, if this, right, and so yeah, you see, it's telling us that it's absolutely convergent. That's what the ratio test is telling us. It's telling us that our series in question is absolutely convergent, which means it's convergent. So it's associated with this absolute convergence. All right, if this limit here is convergent but greater than 1, or this limit goes to infinity, diverges to infinity, then the original series is divergent. Okay? So we can test for divergence as well here. Okay, if this limit is equal to 1, then the ratio test is inconclusive. That is, no conclusion can be drawn about the convergence or divergence of the series we're looking at. So you have to use another test. Okay, so now they go through a proof here of the ratio test. Okay, and so yeah, here this note is just saying that, let's go through this note. The part 3 of the ratio test says that if the limit, the limit of the absolute value of a sub n plus 1 over a sub n is equal to 1, the test gives no information. For instance, for the convergent series, this is a p series with p is equal to 2. If we use the ratio test, this goes to 1. The limit of the absolute value of a sub n plus 1 over a sub n goes to 1, so it doesn't tell us anything. And same for the harmonic series. This is a convergent series. This is a divergent series, but the ratio test doesn't give us any information. If that limit is equal to 1, the original series might converge or it might diverge. So we have to, in that case, we have to use some other test. All right, so here they give an example. We're going to work a bunch of examples, but so the absolute value is going to eliminate the minus 1 to the n, and they do the division. They get this. Take that limit. It's 1/3 less than 1, so it's absolutely convergent. Again, we're going to work a bunch of examples. Okay, here's another example, and we're going to see that when we're going to, in the next section, we're going to work a just general, we're going to kind of bring all of our skills together and work and find convergence of series just like we're given random series. And one thing that the book talks about is that the ratio test is really useful when you're dealing with a factorial. Okay, so there's a sub n plus 1 over a sub n, and right, you can simplify factorials that way. Like n plus 1 factorial over n factorial is going to be like just n plus 1, right? N plus 1 factorial over n factorial. Well, since you can write n plus 1 factorial as n plus 1 times n factorial, then that simplifies to n plus 1. So that's why the ratio test is so useful for factorials. And so this approaches E, which is greater than 1, so this is divergent. Okay, it says, although the ratio test works in the previous example, an easier method is to use the test for divergence. Yeah, so we always want to consider the test for divergence. If we look at a series and we take a look at the sequence of the series, and it seems evident that if we took the limit of that series, it would not be equal to 0, then we can just do the test for divergence and show it's divergent. So you can just look, what they're saying is just looking at this, if you do a little analysis, you can see that this could never be less than n, no matter what. Well, as n goes to infinity, right, then that means that's saying that this limit as n goes to infinity could never be 0, which means that the test for divergence would say that, show that that series is divergent. All right. The following test is convenient to apply when nth powers occur. So we're talking about the root test now. Another test. Its proof is similar to the proof of the ratio test and is left as an exercise in exercise 49. So, okay, the root test. What they're saying here is that what you're going to do is, instead of taking the absolute value of a to the n plus 1 over a to the n, you're just going to take the absolute value of a sub n and then take all of that, the nth root of all of that. And so, you can imagine this is kind of, this isn't that flexible of a test here, but still it's something to consider that if you look at, you could have a sequence that's the entire, if we come here, see this entire sequence formula is raised to the power n. Well, in that case, you can think about the root test. Think about even like you see geometric series, like they're written like this, but in that case, you're not going to need to use the root test because you can just identify it as a geometric series. But I'm just saying that's not that unusual to have an entire expression raised to like the power n. And so in that case, you could consider doing this. You take the absolute value of the sequence that's in the series, and then you put all of that under within an nth root. And then it's the same requirements as the ratio test. If the limit as n goes to infinity, this isn't a series anymore, right? We're taking the limit of a sequence now. As n goes to infinity of this sequence here, this root, the nth root of the absolute value of a sub n sequence, if that is convergent and is less than 1, then the series is absolutely convergent. If that is convergent but greater than 1 or diverges to infinity, then the series is divergent, and it's inconclusive if that limit is equal to 1. Okay, now we're going to talk about these kinds of details in the next section, but it says, so, okay, it's inconclusive if this limit is equal to 1, okay, so the series could converge or diverge. Okay, it says now if L is equal to 1 in the ratio test, don't try the root test, because L will again be 1, and then vice versa. If L is equal to 1 in the root test, don't try the ratio test because it will also be 1. Okay, so these kind of what they just stated here, we're going to talk about these nuances in the next section when we're going to come up with a strategy for if we're given a random series, right, with no context, how do we approach testing it for convergence? All right, so, okay, if they're testing this for convergence, everything's to the nth power, so that they take the nth root of this and they get this here. This is already always positive, so you don't need to take the absolute value. Take the limit, and it's going to be, you can see here, this limit as n goes to infinity is 2/3. That's less than 1, so this is absolutely convergent. That means that it's convergent. Okay, and now the last thing they talk about is rearrangements, and this is the explanation for how conditional convergence is possible. And this honestly is a topic for another video. This could have its own separate video, and I might do that. And all it's saying is that it's an infinite sum doesn't behave in all situations exactly like a finite sum. And they talk about this from their perspective of rearrangements, that with a finite sum, as you know, you could order the terms in any order you want and you get the same sum. But this isn't always the case with an infinite sum. But if you have an infinite sum that's absolutely convergent, then that's the case. But if it's conditionally convergent, then that's not the case. And if you're like me, when I first heard that statement, that seemed insane to me. And so we're going to go ahead and we're not going to go through this here. And I might make a whole separate video on that. But in the meantime, you can just YouTube search rearrangements of infinite sums, and you can see there's explanations on this, good explanations on this. But that's where that's where conditional convergence comes from, right? It turns out that an absolutely convergent series with some s, if you have that, then any rearrangement of the terms of that series has the same sum s. However, any conditionally convergent series can be rearranged to give a different sum. To illustrate this fact, let's consider the alternating harmonic series, and so, you know, they just demonstrate how you can get different sums just by rearranging the terms of a conditionally convergent series. Okay, so again, you might be really confused by everything I've just said. In fact, I think it's confusing enough to where it warrants its own separate video. So if I don't have a video posted on this yet, just do a YouTube search on it. But if I've got a video posted, then check that out as well. All right, let's work some example problems.